We're asked to find the implicit equations of the trajectories of the conservative equation, and then find the critical points and classify them. We're given the conservative equation x double prime plus the quantity x plus 1 times e to the x equals 0. Referring to our notes on the right, if our conservative equation is in the form of x double prime plus f of x equals 0, notice in our case f of x is equal to the quantity x plus 1 times e to the x. Every conservative equation in this form can be written as a system of nonlinear differential equations where we have x prime equals y and y prime equals negative f of x. Where in our case, if we let x prime equal y, then y prime equals x double prime is equal to the opposite of the quantity x plus 1 times e to the x. And therefore the nonlinear system is x prime equals y, and y prime equals the opposite of the quantity x plus 1 times e to the x. To find the implicit equations of the trajectories, because we have a conservative equation, we can use the Hamiltonian, which is the equation 1/2 y squared plus the integral of f of x dx equals c. In our case, we have 1/2 y squared times the integral of the quantity x plus 1 times e to the x dx equals c. To integrate, we do have to perform integration by parts. I'm going to go ahead and show that work, where we have u equals x plus 1, and therefore dv equals e to the x dx, and therefore du is equal to dx, and v is equal to e to the x. Applying the integration by parts formula, the given integral is equal to the quantity x plus 1 times e to the x minus the integral of e to the x dx. If we distribute and integrate, we have x e to the x plus e to the x minus e to the x plus c, giving us just x e to the x plus c, but we already have a constant c in our equation, and therefore we now know the implicit equations of the trajectories are 1/2 y squared plus x e to the x equals c. This question does ask for the implicit equations. If we wanted the explicit equations, we would solve for y by multiplying both sides by 2 and then taking the square root of both sides. This would give us y equals plus or minus the square root of the quantity 2x e to the x plus 2c. And now for the second part, we're asked to find their critical points and classify them. Recall the critical points occur where both x prime is equal to 0 and y prime is equal to 0. We'll notice x prime is 0 when y is 0, and y prime is 0 only when x is negative 1. Notice e to the x is never 0. And therefore we only have one critical point, which is the point negative 1 comma 0. From here, because we have a conservative equation, the eigenvalues will always be lambda equals plus or minus the square root of the opposite of f prime of x. This indicates if f prime of x is less than 0, the critical point is an unstable saddle, and if f prime of x is greater than 0, we have a stable center. Recall f of x is equal to the quantity x plus 1 times e to the x, and therefore f prime of x, applying the product rule, is equal to x e to the x plus 2 e to the x. And now we evaluate the derivative function at x equals negative 1, which gives us negative 1 e to the negative 1 plus 2 e to the negative 1, which is greater than 0. Because f prime of negative 1 is greater than 0, we now know the critical point, negative 1 comma 0, is a stable center. Before we go, let's verify this by looking at the face portrait. To do this, we'll use the online tool referenced below. We first enter the equations, which are x prime equals y, and y prime equals the opposite of the quantity x plus 1 times e to the power of x. Let's go ahead and change the window. Let's change the mins to negative 3 and the maxes to positive 3. Let's also click on the box for variable length arrows and then click graph. Let's go ahead and scroll down. We found the critical point of negative 1 comma 0, which is this point here. Let's click on the graph to show some trajectories. Notice the phase portrait does verify negative 1 comma 0 is a critical point, and it's an equilibrium point with a stable center. I hope you found this helpful.